Okay, so I want to give you guys the fundamental theorems again in summary. Okay, so the first of these is not even from Calc 3. So that one I'm calling recall. Right, so recall the fundamental theorem of calculus, which says what?
That's the derivative junk, right? Or no?
It's a derivative.
Go away.
Okay, it's the one thing I expected you to know from Calc 1.
It's the integral of f.
Oh, the integral from a to b of f.
Yeah. A to b of f.
It's the integral.
Oh,
Okay.
so of little
It's
f?
not two.
No, big f.
You could just say f
No,
prime.
Yeah.
Yeah, we got it.
That does.
So if you integrate a derivative, what do you get?
You get f, little f of b minus a. Little f. Yeah.
Cool. Right, so when you're doing definite integrals, you find an antiderivative, and then you evaluate at b and subtract the evaluation at a, right? You guys all recall this? Okay. What was the interpretation of that? Yeah, that's area under a curve, right? And I'm adding up from a to b in the xy plane, right? So that's dot at a, dot at b, thing in between, you're adding up, right? So you notice that on a, b, right, you do like antiderivative, right? Evaluated at boundary. You guys with me on that?
Okay.
Like that's what the fundamental theorem of calculus says. It says if you want to evaluate an integral over a line segment, right, of a derivative, you can go find the antiderivative for that derivative and then evaluate it at the ends. Cool? Okay. My claim is that all of the fundamental theorems we've done say that same thing. So you might remember that there was a fundamental theorem of calculus for line integrals, right? You guys remember the fundamental theorem for line integrals?
Yeah.
Maybe?
Was it?
Okay, so I think you remember this. So it's if you're line integrating over a curve C, a gradient of a function dotted with dr, right? So this is a line integral of a gradient of some scalar function. What can you do?
F at the beginning of the curve.
Beginning minus
F at,
n
Or
minus
at the end.
yeah, Q minus F at P. And this is me thinking there's a curve C, right? And it goes from a point P to a point Q. So again, what did I do? I went from here to there by taking a kind of an antiderivative. You okay? You guys see that?
Yeah.
Like here to there, I did antiderivative, and then I evaluated at the boundaries. You guys cool with that? Cool? All right, next one. What was our next fundamental theorem that we learned?
Divergence theorem.
Okay. Okay, so the divergence theorem says if I integrate over a solid, right?
Yes.
So I have I'm calling my solid W today because your book calls your solid W. So I'm integrating over a solid W. What am I integrating?
Divergence of vector field.
Divergence of a vector field.
And it's
D what?
It's a volume integral.
Why? This thing is a
Scalar.
scalar, right? well, really it's a scalar function. You guys with me on that? Is the integral over
The surface,
the surface
vector field dotted with the
of the vector field dotted with the area, right?
area vector.
Yeah, with the area vector. You guys all cool with that? Antiderivative, right? But now instead of evaluating at the boundary, you guys see that? Like, here's what I'm thinking. I'm thinking, here's a thing, that's W, right? Like W is this filled in
Sphere.
well, sphere-ish thing, right? What's S?
The surface.
S is the surface, right?
Uh,
That's the boundary, right? So why can't I just take the one end minus the other end? Because it doesn't even make sense, right? So you just add up all the ends. Integrate. You guys cool with that? So again, it's antiderivative evaluated at the boundary. You guys cool with that? They're not gonna be able to see this, whatever. Okay, so what was the other one?
Stokes.
Divergence. There was Greens and Stokes, right? Stokes and Greens are the same thing.
Yep.
Greens is just
Two-dimensional.
Stokes
versus-
with two of the dimensions stripped off. Right? The normal vector in a Green's theorem is always just k. Right? Okay, so my Stokes says what? If I'm integrating,
Over all Stokes.
Yeah,
So-
Surface.
yeah, the boundaries.
I'm trying to set this up the same way I set those up, right?
Oh, so.
So I'm starting with the surface integral of the curl of f d area. That's the integral over,
Closed integral.
yeah, it's a closed integral, right? Over the
What's
curve
boundaries of the surface.
of, what goes here?
F dotted with ER.
F dotted with dr, right? This is a circulation integral, right? So what happened? Well, there's a surface, right, which might look like this thing. What's the boundary of that surface look like?
Just the
Disc thing.
yeah,
Also.
desk. Correct. Just, yeah.
Right? And there's some orientation agreement stuff that I have to make happen with these guys, right? In here, it's kind of, yeah, it makes this picture a little easier to put it on.
What is the S in the diagram for divergence pointing to?
Yeah, so this W is pointing at the whole ball filled in, and this S is just pointing at the skin of the ball.
Okay.
Right? It's the boundary of the ball. It's like the outside edge, right? So here, the boundary on a surface is just this curve around that kind of leftover edge, right? You guys see that? So again, I get a kind of a antiderivative
Evaluate at the boundary, which we can actually say
evaluated at the boundary again, right?
it's a closed line integral. We actually could really just call it boundary of the surface.
You guys see that? So each and every one of these theorems is basically the fundamental theorem of calculus, right? They all go from you're adding up a function, so you go find the antiderivative and evaluate at the boundary. You guys see that? What those derivatives mean is a little bit funky, right? It's like here, I mean a one-dimensional derivative. Here, I mean the gradient scalar multiplied, right, by a function. You guys see that? Here, I mean the gradient dot producted with a vector field. And here I mean the gradient cross product with a vector field, right? So those things are a little funky, but they're all a derivative in one kind of way or another. You guys see that? Cool.
Chris and I were talking about Stokes a little bit on Monday, and you're sort of like taking an anti-derivative sort of, but also sort of like anti-crossing, if you go in this direction. And
Yeah.
How
viable is it to go find something whose, like, how possible is it to find an anti-curl? Is that what you're asking?
Yeah, like wouldn't it be a family, just like a normal antiderivative?
Yeah.
Okay.
You guys see that? So if you find a candidate that has this curl, right, it might not be uniquely determined. That's okay. Cool. So, one thing we could also notice here, it feels like, well, frankly, it feels like I should be able to take Stokes and apply that to here, right? You guys see that? Like, I have all these kind of toys, right? And with them I can change like a line integral of a gradient, right? I can turn that into the potential function evaluated at the ends, right? And over here, like a volume integral of some kind of very specific thing, I can turn into a surface integral. And then I have a way to turn surface integrals into line integrals, right? So like, if I started with, say, I don't know, a volume integral, right? Could I turn it into a surface integral and then turn that into a line integral and then turn that into one of these where I do this potential function business?
We'd have to find
You
a
have to
way to
assume
like
it's
find a
integral.
function that the curl of the function is the original and same with the gradient.
So there's this question of like, can I produce a curl function?
But
You guys see
still,
that?
we talked about this too, but I think we run into a problem with Stokes deals with closed surfaces and Stokes is open sort of chunks of like a blanket, and then Divergence deals with closed
Yeah.
surfaces.
So there's this weird thing, right? Like, if you were able to do that, like if you started with a volume integral, right? And you go to this surface integral, what's the boundary of this closed surface?
Itself.
Right? Like, if you started with a volume integral over a sphere, and then you use the divergence theorem to turn that into a surface integral over the skin of a sphere, and then you try to use Stokes' theorem on that, where's the bounding curve? It doesn't have a bounding curve. You should get 0 out of that. You guys see that? Like, that's weird. There's some weirdness that's like, well, if I take the divergence of something, and then I try to find a thing for which that's the curl, it doesn't seem like it works. You guys see that? Like, there's some weird interplay here. So let's figure out what the weird interplay is.